And we're a nonprofit, tax exempt. Our focus is developing and adapting technology so that all sorts of different kinds of learners in K-12, learners in university, and learners and makers in informal education, or just people who want to investigate things, can do a lot more investigation, inquiry, experimentation, collaboration, and communication, sort of in science and technology and engineering. What I'm here to show you today is the framework that we've been working on. About a year and a half ago, we got a grant from the Google Foundation to take a lot of the work that we had done in Java and redevelop it to work in a browser. We've been wanting to move in that direction for a while, but a great deal of our funding comes from National Science Foundation grants, and they're interested in research. And we develop technology with those grants, but it's very hard to actually make it robust and useful. So I'm talking about something. I needed to pick a short name because I was going to type it a lot. So the project is called Lab, and we're doing basically HTML5 based scientific modeling, visualization, graphing, and probeware. This presentation is up in a GitHub repository, so you can find it later. The slide at the end will show you where that is. We've designed the framework to support multiple different kinds of modeling engines, and I'm using the word modeling a little bit widely. The biggest one, the one with the most number of features, we call MD2D. It's a translation of a Java application called Molecular Workbench. It does a lot of 2D molecular modeling. There are some other model types in progress. One is for a solar system, and we're going to be having some simple climate models in there. Another is a signal generator, and another is for working with probeware. So I did not adjust this for the size of the screen. This is a model that runs. It's basically a two-dimensional simulation of, now this is interesting. I'm not getting it running. So we are going to quickly we'll go to the production site and run it there. So there's a lot of calculation going on here. There are two different kinds of two-dimensional molecules. These are uncharged, these are charged. We're calculating the Leonard-Jones attraction between all of these, for all of them. Those are relatively short range. We're also calculating the attraction due to the Coulomb forces, which are charged forces. Those are longer range. The way this works is you're generally going to see clumping among these molecules and clumping among those, and they don't mix very well. And if you mix them, they will, they will end up separating again. Let's see. So I'm going to move through. This is in the presentation, and I'll make sure it's working there later. Embeddable. So this is basically a relatively simple model where we can adjust we can play God. We can adjust the van der Waals attraction. We adjust it strongly. It forms sort of a hexagonal shape. We loosen it, and they start moving all over. We can change the temperature. And one of the things that you could pretty easily experiment with this is if we change the temperature to here and we turn on charge, we can take a look at how hot do we have to get this to get the molecules to move from a solid state to a liquid state. So I'm going to increase the temperature here, and what would you call it? It's sort of moving to a liquid state there. Well, that's probably a liquid state. We have to get it quite hot. Well, if the molecules aren't polarized, we'll leave the van der Waals attraction the same. We'll lower the temperature. Well, that's obviously a solid. Let's make it a little hotter, a little hotter. We're moving into a liquid domain at a much lower temperature. Let's see. We've got different kinds of, even in the molecular 2D dynamics, we've got something for investigating protein folding. and we can set up different kinds of proteins. Now, it's not real protein folding, but we actually are doing a lot of modeling here to figure out what lines up with what. And here you've got a collection of hydrophobic and hydrophilic things. We could change the solvent type. We'll change it to oil. And when there's going to be a different kind of attraction, a different kind of rearrangement of what's on the inside and what's on the outside. I'm going to... One of the things, so here we got that one. One of the things we can also do with the molecular dynamics engine is actually use macroscopic units. This particular model, and again, I'm having trouble getting it working. One of the things in any of these models, when they're embedded, you can actually click the share link and you're going to get the iframe code. Actually, that's not going to work, so I'll just click on this link, which gives me the embeddable code. The embeddables are designed, these interactives, they're designed to fluidly scale to whatever container you put them in. So obviously, at some point, it's going to get too small to read, but we can see it here. When we run this one, we're instead of using the units in the molecular dynamics 2D, which would be femtoseconds and nanometers, we're using MKS units. And this is for the molecular dynamics engine, this is a very simple model. It's a pendulum and a spring. So it's a springy pendulum, and you can see all sorts of strange things. But we can change the rod length in centimeters and run that again. We could change gravity. We could change the mass of the ball, the spring constant. We can do all of those things to do investigations. These graphs over here are a standard part of what we call interactives, which we'll be talking I'll talk a little bit more. Everything is sort of very nicely scalable. So since I don't know why it's not running here, but I can still move forward, that was the protein folding one. Let's just... We've also got one which is modeling DNA transcription and translation. So this is combining some animation steps with actually some modeling steps also. All of this code is open source under attribution-only licenses, so it's there for anybody to use. And so on and so on. And the engine underneath this can use all sorts of different forms of these kinds of models. Moving to another one. This is one that we've just started working on. It's quantum collision. The 2D molecular dynamics model was not dealing with the energy associated with an atom when the electrons are moving from state to state. So this is the beginning of that. We start this model like that, and nothing special is happening. Let me change it, reset it back to the beginning. I'm going to change the starting velocity. And right now we're moving back and forth, and there's energy changes. One of the things you can do is you can run the model backwards and forwards. You can see the graph is going backwards, and we can examine different points. That's available in all the models. So here's another model in the new quantum dynamics plugin. This is going to allow us to actually, we're starting to visualize photons leaving. This is also in early development. This is to help kids understand about seasons, and it's just the beginning. But it's using a similar particle type engine, but it's a different model type. And basically it's particles with mass and gravitational field. And I'm going to be adding a simple latitude-based climate model to that, so kids can investigate basically at different kinds of tilt and different kinds of orbits. One of the things you can do here is you can, let's change it back to, we'll change it to an oblique orbit. one of the things we wanted kids to do is to investigate what is the relationship of tilt of the planet to seasons, and how does that relate to how far away we are from the sun. In the northern hemisphere, we're closer to the sun in the winter. Most kids would think we're further away because it's quite reasonable to think it's warmer because we're closer to the sun. So here's a simple model where the Earth goes farther away. So I'm not going to, signal generator model type was a way of generating streaming data, but it was really designed to support this model type, which works with sensors. I've got a commercial device here from a company named Vernier, and right now the connection to this is with an invisible Java applet. The software from Vernier, their SDK, is completely public domain, so while getting things to work with Java applets and maintaining Java applets is quite difficult. Richard, would you come up and help? Bring your computer too, because I'm going to be changing the talk over to you. So this is an ultrasonic sensor. I just plugged it in and started up the browser. It's a browser which has Java applets enabled, and as all of you know, it's getting harder and harder to maintain security with Java applets. But let's see, can we start this? And we don't seem to be getting the Java applet working. Hold on.
Don't worry, that's part of the course.
Class.
That's why we're interested in like the gamepad API and all
Yes.
the fun things we can
So
talk about in the browser.
one of the things I will mention, so yesterday in the NodeBots workshop, I did probably the smallest NodeBot there. There's really not much here. I called it LittleBot. But what I did was turn this Arduino into something. It turned itself into a joystick. And I had some simple pot and linear, some analog inputs. And once I turned it into a joystick, I could get data in using the gamepad API. So I'd really like to have all sorts of people be able to measure things more easily. And if you can turn Arduinos into sensing devices and make them pretend to be a gamepad, you can get analog data into your computer, into your browser without any extensions or any Java. So I'm not sure why that's not working. One of the things I would do really quickly, let's quit that. Try reloading the page once more. Okay, so actually, I think I know what the problem is. I'm going to do a quick going to the development site. I think I forgot to rebuild the Java resources on the production site. Are we loading this? Yes, it's downloading now. Okay, so we should be able to run it. So Richard's moving further away. I'm getting distance data. And of course, with a Sonar Ranger, we have that kind of a thing. But we can get all sorts of data. Now it's going to time out because it only goes to about 10 meters. But we're getting that data. Let me quickly go back over to here. So you can find this presentation later online on my GitHub account, steveneb.github.io. If you go to github.com/steveneb, you'll find JSConf 2013. That's the part of the name, and you can find this all later. I'm going to show you just a bit about, let's see, where did we get there? Okay. What do I mean by an interactive? So one of the things, when we're developing models like this, it's different than the form that's often used in many web applications. We've got this particular model here. We've got a set of JSON for defining how it works. It's referring to a model. It's referring to various components. This particular one is very simple. It just has a button component and a very simple layout. I'm going to jump to something which has a more complex system here. So this was that pendulum, actually it's just the pendulum one, not the springy pendulum. I'm going to go down to the interactive and show you. So I'm still referencing a model. I'm also saying there's some options for the model. I'm changing the unit scheme to MKS, and I'm setting what the time step per stick is. I'm deciding what's going to happen on load. I'm going to reset various things, and I'm doing things like resetting an angle. Well, what's unusual here is we're just synthesizing outputs and parameters for this. So in the molecular model, there isn't any output called current angle, but we're synthesizing it. We can then use that later in our components. So we have a slider, which is attached to the property, gravity. But here, let's just take a look. So we got a graph component here, and we're basically saying the property we're graphing is current angle. So there's a lot of headroom in this kind of architecture for developing various kinds of ways that things are wired up. So when we look at this, and one of the, let's see, make it embeddable. This is a molecular model, but we're running it in a MKS unit system. These components are all listening to properties and are modifying properties of the model. The properties are also being sent to the graph. These are synthesized properties when we run them. I'm going to let Richard plug in for a bit because he's got a short presentation on how these kinds of property, the modeling is different. Grab that. I will pick up this computer. There you go.
Yep.
While he's getting onto the screen, I'm going to mention one other thing. You should have this that we wanted to show if we have time.
Okay. So I like to say we
Turn on your.
sorry. So I'd like to say we allow these interactives to let students sort of fork, and anyone really learning something, sort of fork history, and that's a model. And so there's actually, we took a bunch of inspiration from JavaScript MVC frameworks that exist in a slightly different domain for thinking about how to do that. So Stephen talked about this, this Pendulum interactive, which is actually pretty cool because we have all these different things you can explore to see what happens. No, what if I change the length? Does that change the period of the pendulum or not? And I can try to find out for myself. Well, if I go back in time, and I've played with the parameters a little bit, and I can play God, I can adjust the gravity, make the gravity bigger, see if that affects the period. Oh, maybe it doesn't. But I may want to go back in time, back where I was, before gravity changed, see the old parameters that I had, and then pick some other one and adjust it. And so we think of that as sort of forking the history of this, this model. And in order to do that, we took a bit of inspiration from MVC frameworks. This is your sort of canonical example from like Ember, which is, this says, oh, okay, here's my something object, which has a full name property. And, I have two other properties called first name and last name that are real properties on this model. And I want my UI to update when, the first name changes. I want the full name to update, and I want the UI to automatically update. And so that's what that handlebars template is doing. Well, okay, fine. Well, we don't exactly care about your name or how many followers you have. I mean, those are great things, but we really care about like physics and time. And we have these neat interactives that have these properties that are associated with the model, and we want the UI to update automatically with those as well. So in order to do that, we use this property system I'm talking about. So we have automatic UI binding is a more difficult problem in this case. So here's an example. I have a gravitational field. Technically, by the way, if you were to actually work this out, the physics, this is like the gravitational field on a neutron star because it doesn't pull down molecules like that fast. But I want to update the potential energy as the things move around. Okay, fine, but the potential energy is actually like the energy between every two of those things in the model and the interaction of each like object in the model with the gravitational fields. It's a whole bunch of computation that has to happen to update that. Well, what's actually neat is if I update the gravitational field value, even while the model is running, the potential energy is automatically updated. And so how do we do that? And so whatever method we use, and this is sort of how you would do it programmatically, bump up the gravitational field, we have to immediately update the potential energy. But there's no easy way to say what is the relationship between the output and the input. We actually have to recompute a whole bunch of stuff. So in order to do that, we have this concept called invalidation. So if we think about it in a sort of programmatic way of doing some of the stuff I was just showing you, is we could step the model forward 100 steps. That's like 100 ticks or 100 animation frames, and we can seek back to 50. Well, what will happen is we'll update the UI using like saved state, because we're actually like saving like a tape recorder of everything that happened in the past. Then we can step forward. Now we're on step 51. Well, okay, all we need to do is like replay the step that was saved in history. But now let's say we change the gravitational field to twice what it was. Well, now step 52 is got to be different than step 52 was before. So we have to know that we can't just retrieve it from memory. We got to recalculate everything. So we have this concept of the invalidation event. And what's pretty neat about that is that's a really general way of thinking about how to update MVC type properties. So any change to a model property invalidates. It forces recalculation of all the properties. And since you're just in a physics model, you just can't predict what all the relationships will be. It triggers notifications, so you have nice UI binding. And as we just saw, it sort of is smart enough to discard the future history that you are no longer going to see. We have this idea of movement in time, which is kind of fundamental to these models, and something I think that's interestingly different from a sort of standard web app. So they progress in time. And so when you move on in time, we sort of assume everything is going to change, so we just notify everything. And the last thing is these properties give you this neat idea of parameters. So parameters, this sort of UI stuff you saw me manipulating in the Pendulum demo, they're properties too. And all they do is trigger an action. It can be a real ugly action to make the model state somehow like match their value, like by updating the gravitational field. It'll make things act as if the gravitational field is larger. And so here's a really simple model. It's showing like this piston is pushing in and these molecules are bouncing around. Well, what if I add a whole bunch of atoms? I can just move that slider and suddenly any ugly old code I want that makes more atoms show up will actually make more atoms show up, and you'll see you'll bump up the volume of the thing. Well, if I go back in time, or if I do that, I just took away a whole bunch of atoms, but let's say I move backwards. Whoa, I got all my atoms back, and I can play forward what I did. So if I actually really liked having 60 atoms and something really interesting was happening here, I could show that. And so I just think it's a neat, a different way of thinking about what web app properties are like, and I think it may have some applicability to sort of games and simulations and a lot of applications we'll see for JavaScript in the future. Anyway, that's it.
Can you bring up Energy 2D for a second? So I was at the Google Summer of Code Mentors Conference last fall, and I was talking about some of this stuff. And these were people who came to a presentation on how you can do very fast computational simulation in the browser. And I realized after I showed them some of this stuff, and I told them what I was doing, almost half of them didn't actually get what I was saying. They still thought it was happening in some extension or plugin or Java, because they really didn't understand how fast you can do things in a browser. There's lots of great performance in a browser. I'm right now going to be showing something. Here, I'll just pick my favorite one. This is different. This is not yet connected as an interactive, but it is a model we want to. This is a fluid dynamics model. We've got 100 by 100 cells here. We're doing convection, conduction, and a simple form of radiation. There's no radiation in this model. This is showing velocity 1, velocity 2, velocity 5, and velocity 10. what you're seeing down here as turbulence is really the turbulence associated with the kinematic viscosity changes at the different velocities. There's a lot of calculation going on in there. We don't have time to show it, but last summer at the end of the Google Summer of Code work I was doing with Piotr Janik, he re-implemented the physics solvers in here in WebGL, and we were seeing speed-ups of between 4 and 20 times. So if anyone has been doing scientific computation, this is all happening right now in JavaScript in the browser. I just want everyone to be inspired about what you could do actually with this kind of scientific processing, this kind of capacity. So we're probably about 1 minute left. Maybe there's some questions while we pull off our computers. Any questions? What sort of what? Well, this particular one, it's basic fluid dynamics. It's that's why it was easy to, relatively easy to port into WebGL, because it can work in a sort of a parallel fashion. If you go to lab.concord.org, there's a section on Energy 2D, and there's a whole bunch of stuff with a pointer to an article in our newsletter by Piotr about how he did the WebGL conversion. But all the code is there. There's a developer email list, so if you go to lab.concord.org, you'll find links to the repository, links to the developer email list, and I'd be glad to follow up if anyone's interested. I think that's probably the end of our time. If people have more questions, I'm Stephen Bannasch, Richard Clancer. Find us milling around and talk to us. We'd love to have anybody add more model types, work with you to make this work for more frameworks, more models. Thank you.